Morning. Please allow me to introduce myself and my colleague. So my name is Liang Ma. My colleague's name is Zhifei Yang. So basically, we came from the TikTok UK STE team. So the STE team basically covers the TikTok infrastructure globally. So I'm working with DPDK for years and kernel for years as well. So today, I would like to join with my colleague, Zhifei, together to share our journey about how to enable the confidential virtual machine to running the DPDK. It's a very interesting topic. The confidential virtual machine, sometimes people call it different names, like a trusted execution environment. And depending on the vendor, sometimes it's called like TDX and the SEV and the CCA, etc. Right? It depends on the vendors. And generally speaking, the confidential virtual machine basically allows the virtual machine user to protect their privacy without trusted hypervisor. Right? So this is extremely useful in the scenario when the user really care about their privacy, right? Without trust any specific public cloud vendors. So if you check the top tiers public cloud service provider, all of them support confidential virtual machine right now, all of them. So there's one idea jumping into my mind, right? Why not enable DPDK inside the confidential virtual machine, right? So when we started looking into the great details, we just realized, oh Jesus, it's not a trivial, task. That's actually need a significant amount of effort. The reason for that is it's not just DPDK changes. You actually need to understand different the hardware spec and also understand what change needed to made into the kernel, right? So after the months hard working, eventually we made it. Okay, we made it. So today we're going to share some interest findings through the process. Okay. So this is the agenda today. So number one, we would like to introduce, what's the background and what's the challenge, right? After that, we propose a solution, both in kernel side and the DPDK side. After that, that will be, we do some, we design some test case, try to do the benchmark about the performance, and then we try to interpret the result by ourselves. The fourth one will be the conclusion and about the future works. Okay, thank you. So I will hand over the next session to my colleague. Okay, thank you.
Okay. Okay, this works. So I'll start from the background. So confidential computing, as Liang has introduced, it actually produces something called data in use. It enables confidential data processing on untrusted platforms, such as public cloud VMs. So the latest technology enabling confidential computing is called confidential virtual machine, which is just a virtual machine and with some memory encryption enabled. Includes Intel TDX or AMD SEV and ARM CCA. So regarding the notion of data in use, we can see from this picture, traditionally, we have end-to-end description on both data at rest, such as looks block device encryption, and data in transit, such as TLS encryption. But we don't have a means to protect data in use, which is in our CPU chip. And no, not only in CPU chip, but also in the main memory. So every data in the main memory is unencrypted and can be seen or manipulated by the underlying hypervisor, and which is controlled by the public cloud provider. So this kind of work, confidential virtual machine or confidential computing, is to protect such data that is unencrypted on the cloud platform. And the CVM hardware actually does the encryption. It encrypts all memory of the VM using a per VM key. So only the VM guest can read and write the data in the confidential virtual machine. And what happens on the DRAM read and write is that the CPU chip will transparently encrypt or decrypt the data from or to the DRAM chip automatically. And the encryption state is controlled using the page table, which is controlled by the guest kernel. In the page table, we know that the mapping is from a virtual address to physical address using a page table entry. In the page table entry, there is an additional bit called C bit that controls the shared state or the encrypted state or unencrypted state, which here we call it shared or private, because if the data is unencrypted, you can share it with the host, so the host OS can see it. If it's encrypted, then it's private to the VM. So can we really run DPDK in a confidential virtual machine? The problem first comes in is about I/O. So I/O devices only understand unencrypted data. So if you do port I/O or MIO, it's fine because this is, in principle, no DRAM involved. But if you do DMA, which involves the memory, then only shared memory can be used. However, in the confidential virtual machine, almost all the memory is encrypted. So if you run DPDK, DPDK has no way to get unencrypted memory so that it can do I/O with the device. What Linux kernel network stack or Linux kernel in general does is to handle this kind of DMA using the software IOTLB bounce buffer. It maps the software IOTLB buffer using unencrypted memory, and that buffer acts as a relay hub between the shared memory and encrypted memory. But DPDK doesn't have a way to get such kind of unencrypted pages. DPDK has to handle DMA by itself and establish the DMA channel by itself. So DPDK needs a way to allocate and use shared memory pages from the kernel. But does DPDK really need to do the software IOTLB style bounce buffer DMA? We can recall that in a confidential application, we not only need to protect data in use, but also need to protect data in transit and data at rest. So we need to deploy other protocols like LUKS or TLS. And if we enable this kind of protocols, then data coming, let's take the example of TLS. Data coming from the NIC first comes into CVM shared memory, which is in the kernel and not encrypted, because only in that way you can do DMA. So in this stage, the data is TLS encrypted, but not encrypted by the CVM hardware. Then you do a software IOTLB bounce. It comes into the CVM private memory, which is both CVM encrypted and TLS encrypted. So this is actually double encrypted. Only after this, we do a TLS decryption so that the CVM, the application in the VM can use the plain data to do processing. But do we really need this kind of double encryption? The answer is that we actually don't need it. We can directly decrypt from the CVM shared memory into the final destination that we want to use the data. So unlike the kernel, DPDK applications have enough insight about when to use shared pages and when not to use, when it is not needed to use encrypted pages. So this is our solution. We co-design in Linux kernel and DPDK. On the kernel side, we need to support user space allocating CVM shared memory. And then in the DPDK side, we use this kernel API, which is just a system call, to allocate CVM shared pages and explicitly manage these pages so that the applications have an appropriate interface to use them. So on the kernel side, actually DPDK requests a huge page backed memory using mmap. What happens in this kernel is that it creates a virtual memory area, a VMA, and sets the appropriate protection flags, faulting all the pages, and clear all the pages using zeros. So our change is add a new mmap flag called map CVM shared. So when you do mmap, you add this flag, then the VMA will be flagged with this protection flag, and it will fault in the huge pages and set the appropriate encryption state, and also zero the page using the correct encryption state and hand it over to the user space. And in the Linux kernel side, there is already something called COCO, or confidential computing, which is an abstraction layer that abstracts away the differences of different CVM platforms such as TDX or SEV. Basically, the difference is just the position of the C bit and the semantics of shared and private. So in COCO, all of this is handled. So we can simply use a mmap flag to handle all the encryption state change. And in the kernel, there is two APIs called set memory encrypted and set memory decrypted that will do the change. So on the DPDK side, I'll hand it over to Liang because he's more expert here.
Yeah. So after the kernel basically can provide a new mmap new flag to allow us just allocate memory in the shared huge page instead of the private huge page. So DPDK now facing a problem. DPDK basically need a differential with two kind of different memory type. Okay, so we're now facing a challenge. So we have two ways to do that. The number one, we can simply just embed this design into existing DPDK memory management system, right? And another way is simpler. We just duplicate the memory management data structure as another copy. Just use specific memory management data structure just to manage those shared huge pages, and we use traditional one just to cover the private memory type. So we choose the second one. The reason for that is we don't want to mess up existing memory management system, and also we don't want to disturb the normal case performance, because once you embed the new segment type into the segment list, when you scan that whole list, you definitely need to figure out if this is a shared type or this is a private type. Basically, will disturb normal case performance. We don't want to mess up that. So we choose the second one. So basically, we create a specific data structure, and we also introduce the second change. We introduce a new parameter for EL. The reason for that is obviously the application needed to know how big shared huge page they need. Right, so the kernel or the DPDK itself have no idea, right, about that. Kernel and DPDK itself just provide the infrastructure support that, but we still need a user, make decision. For example, if I need, we say 1 gig shared huge page or 2 gig, either way, you need to provide the input. So we basically, add a new EL parameter. The second part is basically we change. In the EL initialization process, we make some changes to specifically initialize all those shared huge page. Okay, we can move to next page. Okay, it's fine. Yeah. So basically, in this diagram, basically we show how the EL initialize all those huge pages. The red part is the change we made. Okay. So first part here, we basically allocate and initialize the shared huge page specific memory management data structure. Basically, that's a clone with the original one, but with different C bits. This is a new C bit to highlight this is shared huge page. The second part is when we try to do the mmap. Original process, we just do one pass, but now we make two passes. The first pass, we use a special flag, special mmap flag, just like this. We map that shared huge page first, shared type huge page first. In second pass, we just do the traditional way, just to deal with the existing stuff. Yeah. Okay, this is a traditional DPDK memory management structure with your huge page, with your segment list, and with your heap, right? So traditionally, in each socket, you only have one heap. So now we introduce 2 heap per socket. The one heap covers the normal case. Another heap actually covers the CVM, shared page, huge page case. Okay, I move to the next one. Yeah. Okay, that's the next one. Yeah. So after that. Okay, obviously we can embed this kind of type logic into the existing DPDK API, like RT-malloc. We can add something like if. That's what kind of type, right? And then you can make different logic. But we don't want to mess up with API compatibilities. And in the future, maybe we can propose some change. But in this moment, still very early stage, we don't want to mess up that. We basically just provide a totally separate new API. This API just does exactly same behavior like the normal API, but only difference is those API only working on that special shared huge page zone. Okay, never touch that existing normal case, normal huge page zone. Okay. Okay, after we're doing this work, I have some kind of feeling is it's not too late to think about, to abstract the memory operations. We can even be more ambitious, right? Because in these days, the heterogeneous memory became more and more and became much common than before, right? Like your GPU memory, like the CXL memory pool, that kind of remote, slow, but cheap memory as well, right? So I feel in some day, DPDK doesn't really need to deal with those memory, no doubt, personally, okay? In my opinion, there's no doubt. We are going to deal with that. And by that way, why not we just abstract the memory operation as a library? Right? We just make another library, yet another library, just to put an abstract layer, and underneath implementation can be hidden, right? So then we can introduce whatever different kind of memory we like. Okay, that's our, it's a little bit off topic, but I believe that's worth to think about now, right? At least, it's some kind of hint for the software vendors and hardware vendors. We can collaborate together, maybe to figure out, how to do that in the future. Okay. Okay, so this is the key for this kind of application. As we mentioned before, for DPDK application, you have to use a shared page to basically allocate all your device like ring, your descriptor, in the shared huge page, and also the first time DMA, because DPDK processing, normally you will have multiple memory pool, but at least for the I/O, device I/O memory pool has to allocate it inside, our shared huge page pool, because that's obviously transparent, that's not encrypted memory zone, right? After that, for example, if you try to apply decryption, you definitely can decrypt that. Obviously, you don't use in-place decryption, but you can decrypt that from this shared huge page and to your private huge page. Do that seamless. Okay. Okay. For the testing, I just hand over this session to Zhifei. Yeah.
Yeah, so after doing all of this work, we want to evaluate the performance of DPDK in a normal VM and DPDK in a confidential virtual machine. And we also want to compare with the kernel network stack as the baseline. So we have these 3 sets of experiments. For the baseline, we just do UDP test, iperf UDP test. And for DPDK side, we do 2 kind of experiments. First, we use a plain L3 forwarding, DPDK L3 forward application to test the upper bound of the performance, the bandwidth. And then we add extra mem copy, actually two extra mem copies between the shared and private memory. We just copy the packet from shared memory to private memory, then copy back from private memory to shared memory to send it out. This mimics the behavior of decryption and encryption between the shared and private pages. So the setup is we use an AMD machine to and enable the all the solution in the AMD SEV environment. The machine has 2 Nimba nodes and 64 cores. We use the upstream latest DPDK, and the kernel side we use pretty new kernel with the AMD SEV patch. So for the SEV guest, we vary the number of vCPUs from 1 to 8. They are all pinned, isolated and pinned on the host, and 16 gigabytes of memory, and using a virtualized PCI NIC to get the theoretically the maximum performance. So for the baseline, this is iPerf test. We use UDP. So on the host, it is the iPerf client which sends the traffic. On the guest, it's a iPerf server. And yeah, all the parameters are shown here. We also vary the number of vertical queues from 1 to 8. And the number of guest CPUs are the same as the number of queues, just to test the scalability. So in this setup, the expected data path is that from host iPerf, it goes into host kernel space and go into the host type device, then comes to the goes back to the host user space to the QEMU vhost, then enter into the guest kernel, then finally into the guest iPerf. So this data path is actually pretty long, and the expected performance is pretty low. So what we can see here is the maximum bandwidth we get is around 10 gigabits per second using 8 queues and large UDP datagrams. The size is about 1,500 bytes. So if we only use one queue and a small package, then we can see from here that the bandwidth is pretty low, just 0.2 gigabits per second, and also the SEV is even lower, maybe because of the bounce buffer mechanism that involves extra memory copy. Yeah. So then comes to the DPDK side benchmarks. On the host side, we use DPDK test PMD as a vhost user backend. And on the guest, we use DPDK L3 forwarding. And the guest NIC is just virtual net PCI passed to the DPDK using VFIO no IOMMU, because this is the only way that a CVM supports VFIO. Currently, we don't know about future. Yeah. So the parameters, we also vary the number of the size of the packets and vary the number of queues and logical cores. Each queue pair is assigned to a separate logical core. So the data path of this test is that in the host side, the host test PMD is running in the host user space. And on the guest side, the L3 forwarding application is running in guest user space. And they share the virtual queue in the shared CVM shared pages. So in this case, there is no extra mode switch or whatever in the communication path. And we can see that above is the L3 forwarding, naive L3 forwarding application bandwidth without any extra mem copy. And below is the modified L3 forwarding, which involves 2 extra mem copies that mimics the TLS encryption and decryption, etc. So we can see that on the plain L3 forwarding test, the DPDK running SEV in worst case is still 17 times the bandwidth of kernel, and 95% of the performance of DPDK running in VM. So there is basically almost no performance loss. And with extra mem copy, there is some small differences. So in the worst case, the DPDK in SEV is still 8 times the performance of DPDK guest kernel performance. And in this case, it's still close to the VM performance, but not as close as the plain case, because now it involves extra mem copies between private page and shared page, and that hardware encryption and decryption that is between the CPU chip and the DRAM actually sometimes becomes a bottleneck. And we can see is that the most apparent performance downgrade comes in when the packet is large, like 1,500 bytes. So, but also the performance degradation varies with the number of queues. So if we increase the number of logical cores, like from 1 core to 8 core, the performance downgrade also drops from 16% to just 8%. So we suspect that this is because, because here we actually tested 1,460 bytes. This is not aligned with the cache line size. So we suspect that this is partially due to the design of the encryption and decryption hardware that maybe involves some behavior of the cache. We need further confirmation from.
Okay, so basically here we don't know the root cause for sure. Okay, but for inline decryption and the encryption, we suspect there is something not aligned. Buffer may introduce some overhead there because the decryption and the encryption normally need a padding scheme. Okay, if you're not really aligned with the block ciphers, block size, potentially will give you some penalty. That's just our guess. Okay, we don't know for sure. We need the AMD CPU architecture maybe help us on that part. Okay, thank you.
Yeah. So the conclusion is that DPDK in
okay, I will do that. Okay.
Yeah.
So today, given the hardware, design and hardware, starters, basically the device I/O in the device I/O performance in the confidential virtual machine is a huge challenge there. So our proposal can be very useful to mitigate this bottleneck. Okay. Because we show our data, so if we apply our solution, the network I/O performance can increase significantly. Even you involve with that inline, decryption, encryption, much better than the default kernel solution. Anyway, right? That's our number one conclusion. The number two, So that's still depend on the hardware characters because different vendor may introduce different design, and with different design give the different restrict on those I/O privileges, and also the different design has different underneath encryption, decryption, inline, implementation. We have not really transparent to us, so we will try our best, maybe collaborate with our friends from all the vendors to conquer that in the future. Okay. So in the future, we still have some work to do. Obviously, number one, we need more testing and analysis result. The number two, we still need to think about how to make that compatible with the secondary process and the legacy memory model. This can be very challenging. And the third one, obviously we need to enable this feature on more hardware platform. So right now, our side code is 100% ready. We still need our, friends in the hardware vendor side to tweak a little bit, just a little bit, not very far away. We are very, very close now. Just take a little bit. Then I believe this will working in the future can working on all major, confidential virtual machine platform. Okay, thank you.
Yeah.
So any question? No. No question? Okay. Okay, if no question, that's fine. Okay, thank you.